Okay, so what I want to go over now is the ionic radius and the trends there, as well as ionization energy and the trends there. So if you look at these pictures here, what I am showing you here is that cations, when we form cations, we compare the size of the cation to its neutral atom. It's always smaller. There's two different ways you could think about this. You can either think about when people lose weight, they get smaller. But if we also think about, here we have sodium, if we were to write the shorthand configuration of sodium, we would see that we have neon, and then we have 3s1. When we form the sodium ion, we lose that electron, the outer electron, and then we just have neon. We look at our periodic table, neon has two energy levels. So this is Na plus 1. This is Na. We started with 3 energy levels. Now we have 2, so it's smaller. If we think about anions, here we have chlorine and the chlorine ion. You can either think about, well, when you gain weight, you get larger. You can also think about what's happening with electrons. Now, when we think about chlorine, chlorine does not gain a whole new energy level when it forms an ion. We start out with chlorine is neon, and then it's 3s2, 3p5. When it forms an ion, we now have neon, 3s2, 3p6. You see there's no new energy levels. However, what's happening is that we have more electrons with our chlorine ion. If you have more electrons, think about electrons repel each other. So if we have more electrons, we have more repulsion. So the ion will be larger, the anion will be larger than the neutral atom. So we have more electron to electron repulsion. Here we have fewer energy levels. So those are the reasons why the cation is smaller than the neutral atom and the anion is larger than the neutral atom. So that's another trend.
Now what I want you to do is to look at neutral atoms versus ions. So try these 4. So once you've tried those 4, so pause the screencast, try those 4, and then again we'll go over the answers. Okay, so hopefully you guys tried those 4 and you have your answers written down. So let's look at, these are going to be ranked from the largest to smallest radius. So here we have argon, chlorine ion, potassium, and sulfur ion. Now remember, when you have an ion, you're going to have to think about what that ion looks like. So we think about argon. Argon has 3 energy levels. We look at the chlorine ion. The chlorine ion also has 3 energy levels. We look at potassium. It has 4 energy levels. And then we look at the sulfur ion. The sulfur ion is going to have 3 energy levels. So one thing I want you to notice is that argon, chlorine, and sulfur, these 2 ions in this neutral atom, all are isoelectronic with argon, since they all will have the same electron configuration as argon. Potassium will definitely be the largest since it has 4 energy levels. So what we need to compare then are argon, chlorine, and sulfur. Now we need to focus on how many protons are in the nucleus of each one of those. Argon has 18, chlorine has 17, sulfur has 16. So that's going to be the difference here. They all end up having the same number of electrons, but they have a different number of protons in the nucleus. So then the next largest after potassium will be sulfur, because it has the fewest protons in the nucleus, pulling in those 18 electrons. The next one would be chlorine, because once again, chlorine has the fewest number of protons, pulling in those 18 electrons. And then the smallest would be argon, since it has 18 protons pulling in 18 electrons. Okay, so let's look at another one. Let's go down here. We have iodine. Iodine has 5 energy levels when it's an ion. Barium will also has 5 energy levels when it's an ion. Cesium will also has 5. Fluorine only has 2 as a neutral atom and as an ion. So fluorine is going to be the smallest since it only has 2 energy levels. Now, if we look at iodine, barium, and cesium, these 3 ions are all isoelectronic with xenon. So these all look like xenon. So I'm just going to write that down here. Isoelectronic with xenon. So here, what we need to focus on, again, is how many protons they all have in their nucleus. Iodine has 53. Barium has 56. Cesium has 55. The number of protons do not change when an ion is formed. Okay, so they all have the same number of electrons, but different number of protons. So, and I apologize, fluorine should be the smallest. Okay, so of the 3 of those, the largest one will be the one with the fewest number of protons, which will be iodine. So that's going to be that will be the least able to pull those electrons in. The next one would have the next smaller number of protons, which would be cesium plus. And then the last one would be the one with the most protons, which would be barium 2 plus. And that would be our ranking. Okay, so you will see some of this in your homework, so just continue practicing, and then we'll go over your answers for those problems next class.
Now I want to go over ionization energy. And first, I want to go over what ionization energy is, and then we'll go over the trend. So ionization energy, or IE, is the energy required to remove an electron from an atom. So it's energy required to form an ion, form a cation. So remember, ion. So ion, we're forming a cation. So here, what I'm showing you is if we have magnesium, already magnesium is going to be in the gaseous phase. So we're assuming they're starting with a gas phase of our element. We add the energy. In this case, it's only about 738 kilojoules. And then we form the cation with a +1 charge. And we have an electron. So we're separating one electron from our neutral atom. We call this the first ionization energy because it's only the outermost first electron. If we remove a second electron, so now we're starting with Mg+1, we add even more energy, form Mg+2. This is called the second ionization energy because we're removing that second electron. So I want to go over what happens with this trend and the reason behind it. One thing I want you to notice right now is the second ionization energy is greater than the first ionization energy because now we're removing it from a cation, which has an even greater positive charge. So second IE is greater than first IE because we're removing it from a cation. which has greater attraction for the electron. Okay, so the patterns that we see with the ionization energy is it increases going up a group, and it also increases going from left to right on periodic tables. We'll go over these two reasons. So the reason why it's opposite of the radius is if you think about if we have smaller atoms, the valence electrons are closer to the nucleus, so the attraction between the nucleus and those electrons is stronger. So we have less of a shielding effect, and we'll go over what shielding effect is. There's also some situations where we have very stable configurations where we don't want to lose an electron, and we will see some jumps in some cases because of those very stable configurations. So shielding effect is shown in this slide. If we think about lithium, lithium has 2 core electrons and has 1 valence electron. So there's not much kind of blocking that nucleus and the valence electrons. So the valence electron really feels the pull from that nucleus very strongly because there aren't many electrons between that valence electron and the nucleus. We compare this to potassium. Potassium also has 1 valence electron, but has 3 energy levels in between that valence electron and the nucleus. There's a lot of stuff between that valence electron and the nucleus, so valence electron won't feel the attraction of the nucleus as strongly because there's so many energy levels in between. You could also think about if you were protecting a plate of cookies, if the cookies were right next to your body, it'd be very difficult for someone to come up to you and steal a cookie from your plate. But if the plate of cookies were all the way across the room, it'd be very easy for someone to come and buy and steal one of the cookies. It'd be much more difficult for you to protect those cookies if they were all the way across the room. So another name for those core electrons is also called kernel electrons. So kernel electrons or core electrons kind of shield that valence electron from feeling the pull of the nucleus as strongly. We also have repulsion between the kernel electrons and the valence electrons. So if there's more repulsion because of more electrons, then it's easier to remove that valence electron. So as we go down a group, the shielding effect increases. Okay, before we go over the successive ionization energies, I also want to go over why the ionization energy changes the way it's across a period, going from left to right, why it's the opposite of the radius. So going from left to right across a period, you're getting more and more protons in your nucleus. So you can imagine if you have more and more protons, but you do not have more energy levels, the attraction between those protons and the electrons, since you have more positive, more negative charge, is going to be greater going from left to right. And it's going to take more energy to remove an electron. So we have more attraction between the greater number of protons going from left to right. So it's going to take more energy to remove each electron going from left to right. This is why the ionization energy's trend is the opposite of the radius. So let me just, I'm going to actually ink that onto this slide so you guys can write that down in your notes. So going from left to right. So going from left to right, you have more protons and more electrons. So more attraction between them and greater ionization energy.
Okay, so let's practice ranking ionization energy. So I have these problems here. So I want you to write these down and try these. And then we're going to go over the answers so you can pause the screencast. Okay, so let's go over the answers. Now remember, ionization energy trend is going to be the opposite of the radius. So it's really important to think about the radius. So if you're looking at magnesium, sulfur, and silicon, I want you to think about how many energy levels each of these have, just like we've been doing. And then if they have the same number of energy levels, look at how many protons are in the nucleus. Now, magnesium has 3 energy levels. Sulfur also has 3. And silicon also has 3. So these are all in the same period. So this should be pretty straightforward. You just need to look at the trend for ionization energy. Remember, it's the opposite of the radius, so it goes up, increases going up a group, and increases going from left to right. So here we notice that sulfur is furthest to the right. So of the 3 of those, that's going to have the highest ionization energy since it has the most protons in the nucleus. So it could pull those electrons in more, so it'll take more energy to remove them. Silicon will be the second highest, and magnesium will be the lowest. Okay, look at calcium, barium, and magnesium. These are all in the same group on the periodic table. Magnesium is at the top compared to the other 2. Barium is close to the bottom. So barium is going to have the lowest. So it'll have the most energy levels between its nucleus and those outer electrons. So it'll be least able to hold on to those electrons. Calcium will be the second lowest. Magnesium will be the highest. Look at bromine, chlorine, and fluorine. These are also in the same group. So bromine has the most energy levels, chlorine the second most, fluorine the least. So bromine will be the least able to hold on to its electrons because of the large number of energy levels. Chlorine has the second most energy levels. Fluorine has the least number of energy levels, so it'll be the most difficult to take electrons away from fluorine. Look at barium, copper, and neon. Barium, copper, neon, these are in different groups and in different periods. Barium has 6 periods or 6 energy levels. Copper has 4. Neon has 2. So barium is the largest. Neon's the smallest. Also, neon, you're taking electrons away from very stable configuration, so that's going to have the highest ionization energy. Then we have barium is going to have the lowest because it has the most energy levels, and copper is going to be in between. Okay, so let's do the last one here in E. Here we have helium, phosphorus, and silicon. So again, want you to look at how many energy levels, and then if they have the same number of energy levels, look at the number of protons in the nucleus. Helium obviously has the least. It has only 1 energy level. Phosphorus has 3. Silicon also has 3. The other thing I want you to think about, helium is a noble gas. It's going to take a lot of energy to remove an electron from helium. So helium is going to be the highest, not only because it's a noble gas, but because it's also a very small atom. So it's going to take a lot of energy to remove that electron, no matter what. Then we have phosphorus and silicon. Phosphorus has 15 electrons in the nucleus. Silicon has 16. So they have the same number of energy levels, but silicon has more protons to hold on to those electrons. So it's going to take a little bit more energy to remove an electron from silicon than it would for phosphorus. So silicon would be the next highest, and phosphorus would be the lowest. You notice here this is also the opposite of the radius, so we go from the smallest radius to the largest radius. Okay, so try the problems I assigned you for homework. If you have questions, just feel free to email me.